Good afternoon, friends, and okay, got it. Okay. Good afternoon, good afternoon, friends and newcomers. Welcome to the South Orange Library Fall Lecture Series, Special Conversations with Special People. I'm Phyllis Calvin. I'm so happy to have a very special guest speaker, Dr. Amber Doiron. Things have changed so much since I began these programs over 36 years ago, not only because of the internet, but because now women are finally able to use and utilize their talent and brains to benefit all of society. Today, Dr. Amber Doiron, who is brilliant and professor of electric and biomedical engineering at the University of Vermont, where my darling and beautiful granddaughter Sarah goes, and who has told me about her. And I said, I have to, first of all, the worst thing is I called you instead of doing everything the way everyone else does by email. But anyway, Sarah told me about this wonderful teacher and how inspiring her lectures have been to her and to all who are fortunate enough to have you as their teacher. Words that sound foreign to most of us, we will learn a little bit about today, I hope, such as biomaterials, nanoparticles, and molecular imaging, and what is used for detections and treatment for coronary heart disease, infections, and cancer. I chose the title for today, as I told you, A Woman in STEM, which stands for Science, Technology, Engineering, and Mathematics. I should really say a successful and brilliant woman in STEM. So now it gives me great pleasure to introduce our very special guest, Dr. Amber Doiron.
Thank you so much for that introduction. That's amazing. It's truly my pleasure to be here today. It's always fun to talk to folks that are don't have to be there for class, but are just interested in the topic. So, well, Phyllis, I didn't verify this with you, but I assume it's okay if I share my screen and share a couple of pictures along the way?
As long as you explain it, because most people will be on the phone. Okay.
Yeah, absolutely. So I prepared a couple of slides just to show pictures mainly of a few things that I do and, you know, help me remember what I'm talking about. But for the folks on the phone, I'll try to be as descriptive as I can, certainly. Hopefully my screen wakes back up. I don't know what happened there. Are you folks still there?
Yes.
Yeah.
Yes. Yep.
Yeah.
Okay. I don't know what happened. I lost you for a minute.
The screen is
well, sorry for the
there it is.
Okay. I don't know what exactly is happening. Let me see here. Sorry, everything's kind of freaking out on my end, whether or not you see it or not. Let me bypass this. Okay.
We see it.
We see it.
Perfect. Okay, if you can see my screen, then I'll go for it. Thank you for verifying that. So thank you again, Phyllis, for the invitation, and getting to talk to you folks really is, you know, a wonderful part of my day. So as Phil said, STEM stands for Science, Technology, Engineering, and Math. And I do want to talk to you a little bit about the research that I do. But of course, I'm trying to be cognizant of the fact that some folks in this group may not have taken a science class, or if they did, it may have been a very long time ago. And, you know, sometimes I feel like that talking to my students, it's like, you know, they'll ask me a question. I'm like, I know I learned that at some point, but it's been 20 years since I took that class. So anyway, I want to start out with just a little bit of information about me. If you were on the call a little early, you already heard me say this, but I grew up in Colorado, and I stayed in Colorado to do my undergraduate education. And, you know, when I left high school, I really didn't know what I wanted to do. It was, as for a lot of young folks I talk to on a daily basis, it can be a really confusing time to try to make what are really big, important decisions in your life. And I started out on one track and that didn't seem to fit me. And eventually I kind of found my way to doing chemistry, and I got my undergraduate degree in the chemistry department at Colorado State University. And I found chemistry to be really, really interesting. Studying chemical reactions, to me, helped me envision how the world around me worked. I started realizing that really the way that I looked at the world, I always had this curiosity for what is the chemistry behind that process, or what exactly is going on there at a molecular level. And so that was a topic that I really enjoyed diving into. But what I found a couple of years into studying that topic was that I wasn't sure what I wanted to do with it. Great, I understand about chemical reactions, but how can I actually affect the world with what I'm doing? And I really found my niche in a field called biomedical engineering, which is what I do now, which is a very exciting field that bridges topics from chemistry and biology and engineering and medicine. But at its heart, it's really taking the principles of engineering and trying to apply them to medical problems. So a great way to state this is that engineers like to solve problems. We see what looks like a problem around us, and we can, for example, build the bridge that, brings two sides of the river together, or, numerous applications across mechanical aspects and electrical aspects. But biomedical engineers, we specifically look for problems that are happening perhaps at the doctor's office or in a hospital setting or in an operating room. And we try to apply the same kind of principles of the underlying science to that medical problem. So I'll share with you a little bit later about my particular area of research, but one application of this is really understanding the materials that go into so many of the devices that probably a lot of you, and I know certainly me, that we've interacted with in a medical setting. This can be everything from a simple tongue depressor all the way up to advanced things like a pacemaker, or detailed surgeries that take a long time to do, and maybe you're putting in something like a hip replacement or knee replacement. All of those surgeries and devices and advances have taken years to really come together. And they come together because engineers can take knowledge from lots of different places and put them into these applications to have the right materials that have the right strength to work in that knee replacement, or that come together in order to let a hip implant move in the right way as you walk. And so, anytime that there are issues like that in the hospital setting or in the medical field, that's a place where we can plug in. So going back to my journey, when I learned about biomedical engineering, it was just so exciting in terms of knowing that I could apply the things that I was learning about in class to something that was actually going to help someone. And that was a way that I could really connect my interests into, what I felt was giving back to society through the means of improving medical devices. So I had a really neat experience as an undergraduate. So doing my bachelor's degree in chemistry, I met a professor named Christina Rinker, and Dr. Rinker really took me under her wing in terms of mentoring me. She allowed me to work in her research laboratory, a little bit of which you see right behind her. And I started to learn how to do things like, grow certain types of cells in petri dishes so that we could understand the mechanisms behind how they were working. Learned how to use a microscope. I learned how to do lots of different things that allowed me to use my hands and discover new things and learn new things in this research laboratory. So through that experience, Dr. Rinker really mentored me and led me to go to my first national conference that was all about biomedical engineering. You know, sometimes you feel like you're, you know, an island in the middle of the ocean in terms of what you're studying or what you know, and being able to get into a conference room with 2,000 other people who do the same things that you do is really an inspiring thing. And especially at that age, I found that to be um, just incredibly encouraging. And so the fact that Dr. Rinker was able to take me to that first conference where I could see kind of this world of research open up in front of me allowed me to pursue the next set of opportunities that I undertook. And so my next journey was applying to graduate school, and that was a huge decision in terms of, you know, knowing that I wanted to work in science and getting that advanced degree. You know, to give you perspective, a lot of times women are certainly in the minority of these classes I was taking, especially as a chemist, as an undergraduate chemist. My class sizes were around 15 to 20 people, and typically there were 2 to 3 women in those classes. And so sometimes you feel like you are, you know, maybe a little isolated. But what was awesome was once I got to grad school, um, I started studying biomedical engineering in particular. And biomedical engineering is, I think, the only, or well, I know it's the only engineering major that tends to be almost half women and half men, which is really interesting when you compare that to something like electrical engineering, which tends to be, you know, maybe a handful of women in a larger group of men in terms of the profession and in terms of majors. And so again, at UT Austin, I was really fortunate and was able to get a couple of wonderful mentors that really led me through that process. And getting a PhD was very challenging. To be completely honest, I almost dropped out my first semester there. It was a very intimidating prospect, difficult classes, living somewhere new by myself. All of those things were really intimidating. And, you know, adding, you know, feeling like I was, you know, in a smaller group of women just put more pressure on that situation. But I was really fortunate to be surrounded by classmates. We had a class of 8 people that started at the same time, and 4 of us were women. And that really helped because we bonded very quickly. And a couple of those folks are pictured here. I know some of you can't see this picture, but it's me and a group of 3 other ladies, and we all went to grad school together. And we worked on different projects and got to be experts in different things. But one thing that really helped all of us was the fact that we had such a strong bond together, and that when one of us was going through a challenging time, you know, others could step in and really encourage us. So, you know, I think, you know, the way that Phyllis titled this presentation, "A Woman in STEM," you know, for the most part, I don't know that I've had a more challenging time as a woman in my pursuits than a man might have. You know, we took the same classes, we went through things that were similar levels of challenge, but I was very fortunate in that I was surrounded by other strong women who were pursuing similar things. I was mentored throughout the process, both by women and men, that really led me on, you know, this journey of mine. So after I got my PhD, I decided that I needed even a little more training, which is a lot of times pretty typical in preparation for an academic career. And so I started doing what's called a postdoctoral fellowship at the University of Calgary. So this was a really interesting shift in my life, moving internationally. Calgary is in Canada, and is a really similar place actually to where I grew up, near Denver, and it's right up against the Rocky Mountains. Lots of cool things to do in Calgary, and what I got to focus on there was both working in an academic lab where I had my hands on the microscope, or growing cells or making new things, but also I got a chance to partner with their hospital system, which was right on campus, and get to do some things that were more connected to patients, which was super exciting for me, and gave me some good experience in terms of knowing what I wanted to do next. During that postdoctoral fellowship, I actually ended up starting a small company with a couple of my friends from grad school. And if you're seeing the slides, you can see our little logo there. We called ourselves Nanopulse Biosciences. And I'll get into a little bit, nano stuff here in a few minutes, but we were trying to make and sell nanoparticles for biomedical applications. And we were so excited about our ideas and really passionate about being able to improve human health and improve existing medical procedures and devices. But starting your own business is pretty tough, and we did have some significant challenges. We ended up operating for, I think, 4 years in total, during which most of our work was about trying to get capital, trying to get money through the door so that we could do what we wanted to do in terms of developing devices and nanoparticles. And our company ended up, we decided to close the company. It was taking so much time, and all of us were trying to pursue other jobs, and we decided to kind of close the doors a few years ago. But I got so many cool experiences through doing that. One of the earliest things that I got to do that was just so neat was me and my best friend from grad school, Dan, we got to fly to Japan and pitch our ideas to a Japanese company that was looking at investing in our company. And that was a really neat experience. I saw very little of Japan. We were, if you added up the hours that we were on the flights to get there, we were on flights longer than we were actually on the ground in Japan to pitch our ideas. So it was a very interesting experience, to start the company and try to get money. We of course had some, but it's always balance of financials when you're trying to start a small company. So that was a really interesting experience, but it did teach me that I really wanted to stay in academia, to become a professor. And the thing that was really key in that kind of clued me into that insight about myself was that I missed working with students. Even though I had been a student or a trainee through all those previous years, I was getting to work with more junior students and mentor and show them how to use things in the research lab. And I really missed that when I was working on the company. So I ended up applying for jobs in academia, and ended up at Binghamton University. Some of you may know it, in upstate New York, southern tier, and stayed at Binghamton for about 6 years, and then transitioned here to University of Vermont. And so again, if you're seeing the slides, you'll be able to see a couple of pictures of my research laboratory right now. There are lots and lots of little pieces of equipment that allow us to make new materials in a safe way. So we make nanoparticles, and we make materials that can turn into basically large fancy band-aids. I'll tell you a little bit about those shortly. We also have equipment to grow cells in petri dishes in order to allow us to do some tests to make sure our materials are safe, because that of course is of highest importance when you're doing a medical application that you want to improve someone's life. You of course want to make sure that those materials and those things you're making aren't damaging anyone's health. So again, a couple of pictures here to show a few of the folks. Oh,
Sorry, can I interrupt real quick? I don't think your slides are moving on the screen share. Can you restart the screen
Yeah,
sharing?
that's what I was gonna say too.
It's been on the same thing.
There.
Okay, that's better. Thank you.
Sure. All right, hopefully, sorry, something's weird on my end, but okay. So I just have a couple of pictures here of students that I've gotten to train as part of my job. And, they work in the research laboratory with me. They get to have their hands on the microscope and the cell culture stuff and building materials. And they then present their data at conferences, which is what the two pictures are showing right now. And then hopefully eventually they graduate, which is I'm showing a couple of folks graduating with their PhDs here, and then the two men standing next to them, one of them has already finished his PhD and the other one will finish in the next 6 years. Sorry, 6 months, not 6 years. He'd kill me if I kept him around for 6 more years. And then the other panel here is me in the classroom, and that's really what I love most about this job, is getting to hang out with the younger folks that are excited about science, that are excited about improving people's lives through biomedical engineering. And what you're seeing in particular, I don't dress in a judge outfit every day, but I was dressed up as Judge Judy so that I could adjudicate a trial about medical devices, which was a real case, but obviously we were doing a little mock trial activity in class. But those are the days that I love most. Those are the fun days when I get to see the students learn and be passionate about what they're learning, and knowing that it's real things that could affect their life and hopefully other people's lives down the line. I should have said this at the beginning, but if anyone has questions along the way, I'm happy to answer them. Or you can hold them to the end and I'll make sure and leave time then as well. But getting into just a little bit more about my research, a lot of times the way that I pitch my research or describe it, those of you that can see the slide can see this. Biomaterials is the area that I focus on, and I'll explain what biomaterials are in a little bit, but the way that I like to pitch it to folks that I'm trying to get excited about science and engineering is that biomaterials are making humans super. And so sometimes if we frame this around the idea of superheroes and some of the wonderful benefits that they get out of materials in the things that they're doing. So for example, Spider-Man is taking advantage of some of the properties of the silk that spiders create. That material that they make is actually very, very strong, and in theory could hold lots of weights, including Spider-Man. Obviously, if it was at a larger scale than what we're used to seeing in spider webs. And I in class sometimes I'll pull examples from, say, Captain America and his very strong shield, the materials that it's made out of, and I can make links in class to those kinds of things. So sometimes it's interesting to think about these materials as making humans super. So what do I mean, in terms of real life? How does that affect a real person? Well, biomaterials are materials that are focused on detecting and or treating disease or dysfunction by improving the function of the human body. So I already gave a couple of examples. These might be things like a knee or hip replacement, where the person getting this device is overcoming a limitation of their own body, and gaining these somewhat superhuman abilities, in that we can overcome some of these detriments that may occur as we age or get an injury, or are overcoming a disease. Biomaterials are also the materials that make up things like contact lenses or dental devices. All of these materials are interfacing and interplaying with the normal tissues in your body, and they have to be safe. They can't kill off the cells. That one's pretty obvious, but they also can't really modify the functions of your normal cells or normal organs in an inappropriate way. So some of the advancements in this field are moving into areas where we can design things like artificial skin. That's a product that's already on the market that's used to help burn patients or patients with chronic wounds where they won't heal. We also, as a field, are working on something called a heart patch, which would be helpful if the heart starts to lose function, say in the case of heart attack, where some of the heart muscle dies off. If we could create out of a material a little patch made out of soft, squishy material that could go onto the heart and recapture the function of that heart muscle, that would be a huge advancement in terms of improving outcomes from heart attacks. The field focuses on, if you can think of a medical application, there's probably someone involved in biomaterials that is looking into it. My area in particular is in nanoparticles, and I'll talk to you a little bit more about those in just a second. So I listed a couple of other examples of biomaterials here. Probably a lot of us on this call have some sort of biomaterial that's interfacing with our body currently, or perhaps has in the past. Younger folks a lot of times have braces. Those braces have to be made out of materials that are what we call biocompatible. So all of these materials that were designed, one of the most important properties of them is that they're biocompatible. And if we break down that word, on a really basic level, it essentially means what it says. We want the material to be compatible with the biology or with the body. And this ends up being important not just in toxicity concerns. Clearly, as we talked about just a minute ago, we don't want the material to kill tissues, but we also want there to be an appropriate response to that material. All right, so my research is primarily in the area of nanomaterials, and nanomaterials are something that you may have heard of, especially in the last couple of years. I'll talk about the COVID vaccines with relation to nanomaterials. So nanoparticles basically are particles of material that are very, very small. These can be naturally occurring, like say, if you're standing in front of the ocean, the little droplets of water that might hit you that are vaporized, those might be at a really small level, a nano level, and you might breathe those in, and that does no damage to your body. Nanoparticles can also be designed, if they're not naturally occurring, to accomplish a bunch of different potential things in the body or elsewhere. So nanoparticles have applications in tons of different industries, say like the solar industry. They can be put in solar panels to better capture sunlight. They can be used in heating and cooling. They can be used environmentally to try to clean up toxins. But my research really focuses on how can they be deployed in medicine in order to help a patient. There are a lot of things that we can change about a nanoparticle, like say its size. It can be extra small, be something like 1 nanometer, all the way up to 1,000 times bigger than that, 1,000 nanometers. but that 1,000 nanometer feature or particle is still so small that you can't see it. So we're talking about materials that are so small that they can actually potentially move through your bloodstream, or they could interact with an individual cell. And so the fact that they're so small gives them a lot of advantages that we could potentially take advantage of in a medical scenario. So one that might come to mind is delivering a drug. So these nanoparticles are larger than your typical drug, but much, much smaller than your capillaries or your vasculature. The blood flow is capable of carrying these particles. And so if we attached a drug to the particles, we could affect where that drug goes in your body. A lot of research has been put into being able to better deliver drugs like chemotherapy drugs just to the tumor. All of us probably are aware of how difficult it is to go through a round of chemotherapy on the person receiving that drug. That chemotherapy doesn't just affect the tumor, it also can affect your other tissues. It might affect your hair follicles, and make your hair fall out. It might make you really nauseous. All of these effects are happening because that drug is going somewhere other than the tumor. If it's going to other tissues in your body, it might be killing off cells or affecting cells in those other places and causing those side effects. Well, none of us like these side effects, of course, and nanoparticles can help to get that cancer drug, the chemotherapy, just where it needs to be, the tumor. And so there's been a ton of research over the last several decades on how to get nanoparticles directly to that tumor. And there are a few of these products that have already reached the market. They've been FDA approved, and they might be used in certain types of cancer in order to get better patient results, extend a person's lifetime, put them into remission. Better delivery of that chemotherapeutic drug can really help accomplish that. So my lab has worked a little bit on cancer. A lot of what we work on is in different areas, though. I'll very briefly talk to you about a couple of our research topics, but first I wanted to do a little bit of an aside and talk a little bit about COVID vaccines, because this actually overlaps quite a bit with nanoparticles. So whether you've heard or not, if you have received one of the Moderna vaccines or Pfizer vaccines, these two vaccines are based on nanoparticles. They're delivering something called mRNA. This mRNA helps your body mount a response to the virus if it encounters the virus later. But the first step of this process is putting the mRNA in a little nanoparticle. And then it's these nanoparticles that actually get injected into the body. They dissolve, they fall apart, and then that mRNA is delivered to the place that it needs to go. So this is I think Sarah took my class where I talked all about nanoparticles for a whole semester. This is one of the coolest things to happen to nanoparticles and our industry overall, because it's such a huge impact on our society in terms of being able to improve our immunity, to fight this awful disease that has resulted from the virus. And nanoparticles,
Where are you going, honey?
the technology behind nanoparticles was really at a stage where it was just perfectly timed with this virus coming on the scene. So we're so fortunate that our advancements in science allowed for this nanoparticle technology to come into play very, very quickly. Now, just to be clear, I myself haven't worked on this vaccine. Those were things worked on in companies that could get the technology out really quickly. But after studying nanoparticles for the better part of the last 20 years, I like to think that some of the discoveries that I made or some of the things that I worked on, amongst many other people, helped to contribute to our knowledge that allowed an advancement like this to occur. So to give you a perspective on this, once it was recognized that the virus was proliferating so badly in the very first parts of 2020, it literally took less than a week for scientists at these companies that offered the vaccines to develop the nanoparticle and put the right mRNA in it. It took a week to develop that because we have so much research that shows us how to do this. We've been studying it for several decades and know how nanoparticles work, know how to make them, know how mRNA works, and we were able to put it together very quickly as an industry. Now that, of course, took over a year to test before it was actually going in people's arms. But the actual, making the first vaccines that then could be tested happened very quickly because of all the research that's been done before that. So I'm happy to, answer questions around that if you folks have them. But again, just full disclosure, it wasn't a technology that I specifically worked on. It's just something that I know a lot about because my research is really close to it.
Amber, could I ask a question about that? Was the COVID vaccine the first vaccine to use nanoparticles in delivering medicine?
Yeah, it's the first nanoparticle based vaccine. Yes. I guess there's a little bit of gray area in terms of how you actually define a nanoparticle. So some people that define it a little bit differently might say that a couple other vaccines have used this technology, but this is the one that's purely based on taking something, putting it inside of a nanoparticle, and having that create an immune response. And the really exciting thing is this same technology can be applied in a lot of different ways for other diseases as well. You may have heard of development of vaccines for HIV, for example, or a whole bunch of other things that are in development. In fact, even some cancers could be eradicated or significantly decreased with cancer-specific vaccines. Now, that doesn't apply to all cancers because cancers aren't viruses, but some cancers are caused by viruses. So the potential for this technology is really wide-reaching and exciting.
Wow, thank you.
Amber, I just have to say, number one, it was so fascinating that anyone who is listening has learned so much from you. I appreciate that so much. And I'm so thrilled that my Sarah is involved in something so special and so wonderful to help people all over mankind. And having you as a professor has to be so special. And when she told me about you and what she's learning with the Petri dishes and so forth, and the work that she's doing, it's like something that you can't imagine in today's world that they're doing. And I just have to ask you a question. Who pays for this research? In other words, would the drug companies go to the universities or vice versa? And is it something that's worldwide? All your information that you gather, where is it given out to?
Yeah, that's a great question, and it's a complicated answer, but most research that happens in the university is paid for by the NIH, so National Institutes of Health, which probably all of us have heard of lots of times in the last couple of years. So the NIH gives out research grants for work like mine. I've been funded a couple of times by NIH. We also get money from the National Science Foundation, which is another government-sponsored program. NASA gives out research grants. So all of these are going to be tailored towards what they want to accomplish. So NASA obviously has different goals than the National Institutes of Health. So most research that happens in a university is sponsored by one of those larger government agencies. And other countries have similar organizations. Canada has its whole set of organizations that also provide funding to those researchers. And then there's some funding from places like the American Cancer Society, and a handful of times, although it's much more rare, companies might pay to have their particular thing studied in a university lab. Everything from a new lotion and how it affects human skin to, advanced devices, or all kinds of things in the solar industry, or, things like that, that company can say, hey, I have this thing, can you help me study it in a specific way? But by and large, most of our money comes from the larger government sponsors.
And do you get to choose what you want to work on? Almost.
Oh, that's a tricky question. In theory, I do. I get to choose what I ask for money to do. So I get to come up with the ideas and ask the NIH or ask the NSF for money. But whether or not they give me that money comes from their motivations in terms of perhaps advancing health in a certain direction. So a few years ago, there was a big initiative around, I'm blanking on the name of it, but it was all about brains and brain research as related to Alzheimer's or brain cancer, or different initiatives around that. So if the NIH decides they want to fund brain work, my ideas, however great they might be about, I don't know, heart disease or something, are going to have a hard time getting funding. So in theory, I come up with my own ideas and get to do what I want, but I do have to tailor that to where the money is.
Yes. I had, in fact, he'll be speaking in a few weeks, an investigative reporter who told us about, because of the more recent wars, to the amputees and people who lost either their arms or their legs. And it was much easier to fit the right device on legs, but the arms, and that was very difficult. And they had work probably like what you would be doing to make life easier for the bending and the movement of the, right?
Yeah, the more complex the body part, the harder it is to replace in a functional way. I can certainly go make something that looks like a hand in my laboratory, but if it doesn't bend or twist in the right ways, it's not going to be functional for whoever needs to use it. One of my PhD students, after he finished in my lab, he got to work with a nonprofit organization and go to Africa, Kenya and Tanzania, I think, and he was making prosthetic devices and getting to 3D print them, which is a cool technology where you can make really specific parts. And he was getting to do that for, the little kids there, or the adults that perhaps had an injury and didn't have access to, all the prosthetic devices that we have here. Kyle could 3D print and make, an artificial hand or an artificial foot for those folks there, that then he could just, at the end of the day, give to them, to be able to move forward with. But, hands and arms are significantly more complex than recovering use of a leg or foot.
And do you, with the within the world organizations, do you travel a lot, or because of your knowledge and what you have attained?
I don't do a
In other words,
ton of
is it
traveling.
sharing the knowledge with the rest of the world?
It really varies a lot, researcher to researcher. I certainly have done, a number of trips, and we always like to go to conferences and share what we're doing. and get to go out into the community and share what we're doing. But I have colleagues, the person that I studied with to get my PhD, he travels 300,000 miles a year is what he logs with United Airlines. He's constantly traveling overseas in order to, get to collaborate with folks and share ideas across international borders. And, he's 40 years more advanced in his career than I am. So he gets some really cool opportunities that I haven't gotten to do yet, but I certainly am hoping that that ends up being part of my career. Maybe not that much travel. That's a lot. But it's always so fun to get to go and share ideas and work on things in order to advance human health.
How has his travel been impacted by the all the protocols in place? He can't be doing this.
He is not traveling at all. I think he made one trip in that kind of we all got that window that if we had understood it was actually a window this summer to go do a little travel, and then it got all shut down again. So he's mostly not traveling, especially internationally. He's not going.
Well, at least he got to do a lot before.
Yes. Yeah. He's he's been a great mentor, and he's considered widely as the father or inventor of drug delivery, which is that technology I was talking about where you can deliver a drug just to a specific area of the body. So he started working on those kinds of ideas way back in the 60s. I think he started that kind of research, and it has spawned all kinds of really cool technologies. So there are lots of people with extended lifespans that have him to thank for it.
Could you give his name again? I didn't write it down before. Now I am.
Sure. I don't think I actually mentioned his name before. His name is Nicholas Peppas, Peppas. And he's on Wikipedia, and you can look him up and
It's a
all the cool
Greek
things
name.
that he's doing. Yeah.
Thank you.
Amber, I noticed that you had 3D printing of organs on one of your slides, and I was wondering, is that happening now? That they're able to print?
That's definitely a technology for the future.
Okay.
There have been tons of advancements in it, but it's nowhere near, clinically available.
Yeah.
I think probably 15 to 20 years down the line is when that would be probably a clinically available advancement. But yeah, that's certainly not being used at your local hospital right now.
Does anyone else have any questions?
This was fascinating. Very good.
It was.
Oh, thank you. Thanks so much.
I just wanted to ask you, you're so knowledgeable. Do you have time to write what you're doing, or is all of it every day something new that you have to work on that you don't have time to be an author as well? Being that with the library, we'd love a book by you.
Right.
You're so interesting. I'm ready to buy the book.
You're so kind. I get used to being around people that do the same thing all the time, and so I completely lose perspective on it. But I do academic writing. We publish a lot of our work in academic journals, but I've been told a number of times by a number of people that I should write a book, but I have not stuck pen to paper yet. We'll see.
Take a sabbatical.
Yeah,
no, she's too
that's
important.
What I would need.
No,
We need
get
your
somebody,
work. We need your
somebody to help
research.
you. You
Yeah.
can ghostwriter.
Well, I want to thank you so much. You have really opened up our eyes to the world of science and technology, and that's something that you don't read about. We're not reading books about it. We're not hearing it on the television about, so you gave us the background of everything, and it was so fascinating. And I adore my granddaughter, Sarah, for telling me about you and giving me this opportunity to learn a little bit about how much she's but she has learned so much and is so, I'm so proud of her and her work. That's because you have influenced her so much.
Well,
So,
thank you so much. It's been wonderful to get to share some of this with you folks. And I think you're right. It was actually personally hard on me around the COVID vaccine stuff when a lot of times the credit was given to one person or a couple of people. And I just wanted to yell at the TV and say, hundreds of people have been working on this for 30 years. You know, we got to make sure to share the credit, but it doesn't often get done. But thank you so much for being a wonderful audience and for the questions and everything. It's been great to get to talk to you.
Thank you so
Thank-
much, Amber.
thank
Thank
you.
you.
You're
Thank you.
welcome.
We
And
loved
thank
it.
you. Thank
thanks-
you to
thanks,
Phyllis too. For
Thanks, Michael, for being the
Yes.
implementing the programming. Michael.
And here's another career you could go on. Lectures all over the libraries, all over the
There you
country
go.
in your spare time.
Right, right.
Okay, bye-bye, everybody. Thanks.
Bye.
Bye.